In lecture, we've been talking about covalent bonding and how you can come up with a Lewis structure for various molecules. And you can see I've got some models of different molecules here. So in today's lab, we're going to be drawing pictures of various molecules, but we're going to take it a step further than we've been doing in lecture because we're going to draw three-dimensional pictures. We're interested today not only in how the atoms are connected with each other, but what their angles are. Because the angle between atoms in a molecule can have a dramatic effect on their properties. Changing the angle between two atoms can convert a molecule from a beneficial drug to a toxic poison. So it's important to chemists to understand what the angles are in a molecule and how we can determine those. So let's start out with a simple molecule, CH4, methane. If you were building the structure for methane, logically the carbon would have to go in the middle and the four hydrogens would go on the sides. So if we imagine this center is our carbon atom and these four gold colored balls are the hydrogen atoms, what's the angle between those hydrogen atoms? Well, it's pretty obvious. That's a 90-degree angle. What is it that connects the atom of hydrogen to the atom of carbon? What does this red stick represent? The answer, of course, is that represents a pair of electrons. That's a covalent bond. So each of these red sticks is a pair of electrons. And we all know that electrons don't like each other. They repel each other, and therefore electrons want to be as far away from each other as possible. So the fact that electrons repel each other determines what the shapes of molecules are going to be. They're always going to assume a shape in which the electrons can be as far away from each other as possible. Now, is 90 degrees the best we can do in terms of separating these pair of electrons from each other? Now, chemists used to think that. Until the late 1800s, chemists also thought two-dimensionally. They looked at molecules as being flat. But in the 1880s, a very clever chemist came up with the idea that molecules could be three-dimensional. This is what methane really looks like. It's actually a three-dimensional molecule. This particular shape is called a tetrahedron. Now, in our introduction today, I'm just going to briefly go over these different shapes, and then in the pre-lab video that follows this, I will go into it in much greater detail to help prepare you to do the lab. But if you take a look at this, the one thing that is obviously clear is that the angle between the electrons is now greater than 90 degrees. In a tetrahedron, which is what this shape is called, that angle is actually 109.5 degrees. So the molecule spontaneously spreads out into three dimensions because it allows a greater separation between the electrons. Most of you probably never heard of a tetrahedron before. I never heard of one until I took my first chemistry class. It's not the kind of shape that you learn about in geometry. We learn about cubes and spheres and cylinders and such, but a tetrahedron mainly comes up in chemistry because many of our molecules have this particular shape. The methane molecule then is going to have this particular geometry. It's called a tetrahedron, and this angle is known as a tetrahedral angle. From geometry, we know that if there are four groups or four objects attached to a central point, the farthest apart they can be from each other is 109.5 degrees. So the methane molecule has four groups. Those four groups are the four hydrogen atoms connected to the carbon. Now, similar to the methane molecule is the ammonia molecule, NH3. The nitrogen in ammonia has only 3 hydrogen atoms attached to it, but it also has a non-bonding pair of electrons. So if you look at the carbon, there are still 1, 2, 3, 4 groups attached to that nitrogen atom. Our definition then of a group includes two things. A group is either an atom or a non-bonding pair of electrons. Essentially then there are 1, 2, 3, 4 pairs of electrons surrounding that nitrogen, which means the best angle is still going to be approximately 109.5 degrees. In reality, the angle is no longer exactly 109.5. If all of the groups are identical to one another, then all of the angles will be exactly the same. But if the groups are different, if you have a non-bonding pair and 3 bonding pairs of electrons, the angle is going to change a little bit. In ammonia, it's actually 107 degrees. But for our introductory chemistry course, we're not going to worry about that. We will simply say that whenever there are 4 groups attached to a central atom, it's always going to be considered to be approximately 109.5 degrees. Now, if we remove another hydrogen atom from this molecule, we now have a water molecule, H2O. The oxygen in the water molecule is bonded to 2 hydrogen atoms and 2 non-bonding pairs of electrons. There are still 1, 2, 3, 4 groups, so we would expect the angle to be, again, approximately 109.5 degrees. Now, of course, it's not exactly that. In reality, it's 104.5 degrees, but again, to keep things relatively simple, we'll just assume that the water molecule, the ammonia molecule, and the methane molecule all have an angle of approximately 109.5 degrees. So these are the 3 different possibilities of molecules which have 4 groups. You can either have 4 atoms attached to the center, you can have 3 atoms and a non-bonding pair of electrons, or you can have 2 atoms and 2 non-bonding pairs of electrons. In all 4 cases, the molecule is based on a tetrahedron. We don't refer to this as a tetrahedral molecule anymore because it doesn't actually have 4 atoms attached to the center. So the methane molecule, that is a true tetrahedral molecule. If we remove one of the hydrogens to make ammonia, when you talk about the shape of a molecule, we normally only look at the atoms, not the non-bonding pairs. So in ammonia, there's a nitrogen here with 3 hydrogens down below in a tripod shape. This molecule is referred to as being a trigonal pyramid. It looks a bit like a pyramid. These 3 hydrogens make the base of our pyramid. Nitrogen is the apex of our pyramid. Unlike an Egyptian pyramid where there are 4 points at the base, those are called square-based pyramid. This is a trigonal-based pyramid. And if we remove another hydrogen and make the water molecule, now we only have 3 atoms, the hydrogen, the oxygen, the hydrogen. This molecule is simply known as a bent molecule. I'm not too concerned about you knowing those shapes, the bent, the trigonal pyramid, and the tetrahedron, because many molecules will have enough atoms that there'll be more than one shape in the same molecule, and therefore it doesn't have a specific name. What I'm interested in for you guys in the lab and on quizzes and exams is that you can correctly determine the angle between atoms in a molecule. Now let's consider what molecules will look like if there are only 3 groups attached to the center. This represents a molecule of sulfur trioxide, SO3. While the model kit doesn't actually show it, one of the oxygens has a double bond to the sulfur, but a double bond still counts as only a single group. So whether there's a double or a triple bond, a group is an atom or a non-bonding pair of electrons. And in sulfur trioxide, we have 1, 2, 3 atoms, no non-bonding pairs of electrons. This is a geometric shape you're more familiar with. If you look at this, you'll notice that it is no longer 3-dimensional. Molecules are only 3-dimensional if they have at least 4 groups. So sulfur trioxide is a flat molecule. You can envision there's a circle around this, And we've divided our circle into thirds, and since the circle is 360 degrees, the bond angle here would be 120 degrees. This particular shape is known as a trigonal planar molecule. Planar means flat, trigonal means divided into thirds. If we remove one of our oxygen atoms, we now have the molecule sulfur dioxide, SO2. The sulfur still has two oxygens attached to it, but now it also has a non-bonding pair of electrons, so that would be 1, 2, 3 groups. Therefore, we would expect the angle to be approximately 120 degrees. Of course, it's not exactly. I believe it's about 118 degrees. Because the groups are not identical, the angle will not be the perfect trigonal planar angle. So these represent the two possibilities you can have if there are three groups. Three groups can either be three atoms attached to the center, or it can be two atoms and a non-bonding pair of electrons. In either case, our bond angle is going to be approximately 120 degrees. Our last example will be the case of molecules that only have two groups. A good example of that is the carbon dioxide molecule. We have a carbon in the center with oxygen atoms at each end. Now, the kit doesn't show it, but there is actually a double bond between the carbon and each oxygen. And again, that doesn't matter because all we're really interested in is how many groups are attached to that carbon. We have two atoms. We have no non-bonding pairs of electrons. So two groups, of course, the farthest apart two groups can be would be a straight line. So this particular molecule is called a linear molecule, and its bond angle, of course, is 180 degrees. Now, if you compare the carbon dioxide molecule to the water molecule, they do have something in common. In each case, we have a central atom with two atoms attached to it. Yet the carbon dioxide molecule is 180 degrees, and the water molecule is approximately 109.5 degrees. The key, of course, is these non-bonding electrons. So when you're drawing your structures, whether it's in this lab or on quizzes and exams, don't forget about the non-bonding electrons. If the water molecule did not have non-bonding electrons, then water molecules would be linear. But the fact is the oxygen has two non-bonding pairs of electrons, two hydrogen atoms, that's four groups. That's got to be 109.5. The carbon atom in CO2 has two atoms, but no non-bonding pairs of electrons, and therefore it's going to be 180 degrees. When you work on this experiment on campus in person, we normally use these molecular model kits. This is a student-sized version of a model kit. This is my instructor-sized version, easier to see in a large room. If you're truly interested, I've had students in the past that have actually gone online and bought these wooden model kits. So if you're so inclined, if you want to become a chemist or you just really like chemistry, you can go onto eBay or online to various sites and you can get one of these kits for yourselves. They're pretty simple. The kits have a variety of different colored balls in them. These black balls, for example, have 4 holes drilled in them. These represent carbon atoms because carbon likes to form 4 bonds. These blue balls have 3 holes in them. They represent nitrogen atoms. The oxygen has 2 holes in it, so this red ball represents an oxygen, which wants 2 bonds. And of course, we have a lot of these yellow ones, which represent hydrogen atoms. Hydrogen atoms can only form 1 bond, and hydrogen's pretty common in various types of molecules. We also have some purple and some green and orange balls in our kit. They each have 1 hole in them, and we can use those for elements from group 17. They can be, say, chlorine, bromine, and iodine, in addition to the yellow for the hydrogen, so if you want to be able to differentiate them. Now, to connect the atoms together, we have these little wooden sticks. Most of you are probably way too young to have ever heard of Tinker Toys, but when I was a kid, there were no Legos, there were no Connects. We had Tinker Toys, and that's what these are. These little sticks can be used to connect atoms together. So for example, if we wanted to make methane CH4, we would take one of our carbon balls and we'll put 4 of our wooden sticks in there, representing our 4 bonds, and then we can take 4 of the yellow balls, and that represents our 4 hydrogen atoms. The thing that's neat about these model kits is that the holes are drilled at a 109.5 degree angle. You can tell that they look just the same. It's just a smaller version. It's sort of like Dr. Evil and Mini-Me. So these kits are great for hands-on. Again, you don't need a kit. This can all be done on paper. When you take your next quiz and exam, you will be drawing out pictures of molecules on paper. You will not have a model kit to use. These are mainly just a tool when students are first learning how to do it. If you're having some trouble visualizing 3-dimensional molecules, these kits can be very helpful. If we want to make a double bond, we simply replace 2 of the wooden sticks with a couple of these flexible metal springs. And so we could take, for example, an oxygen atom, which wants 2 bonds, and we could hook that oxygen atom, if we can keep the springs in the molecules. Sometimes these springs tend to pop out, especially when the model kit is getting very old, as this one is. Let's see if we can actually get those springs to stay in here for once. There we go. And now we have made CH2O, and you'll notice, interestingly enough, the model kit is designed so that it now is a perfectly flat molecule. With 3 groups, it should have a 120 degree angle, and it does. It looks just like the sulfur trioxide molecule we had before. And of course, if you wanted to make a triple bond, you would simply take out another one of the sticks and add another one of these wire springs. Now you should be ready to get to work on the lab. So after you've watched this introduction, be sure and watch the pre-lab, where I'll go into a lot more detail in how you can build the molecules and determine the angles, and then you will be ready to get to work. Before we get started on today's lab, I think we should do a bit of reviewing here of the material we were covering in class on how to draw Lewis structures of molecules. Remember, we have a 4-step process, and if you follow these steps in order religiously, you are going to get the right answer. The number one reason students don't get these structures done correctly is because they don't follow the steps in order. So the first step is to sketch out the skeleton of the molecule. That basically means show how the atoms are connected to each other simply using single bonds, just to show what the backbone of the molecule will look like. Our second step is to count the valence electrons. We need to know how many electrons we have to work with because they all have to be accounted for. You can't have more or less than the number of valence electrons that the atoms brought to the molecule. Our third step is to add the remaining valence electrons. We used some of the electrons to build the skeleton. Now we need to put in the remaining electrons as dots. And finally, the last step, which we don't always have to do, is to make multiple bonds if needed. And I put that in very bold, capitalized text because sometimes we don't need it. Students love double and triple bonds. They like to throw them in all over the place, but you don't want to use them if you don't need them. Let's go ahead and work through a practice problem to see how we can apply the 4-step process. So we're going to draw the Lewis structure of C2H2O. Our first step, of course, is to come up with a skeleton for the molecule. And we learned in class some rules of thumb that can help us design our molecule. First of all, we commonly want to put the atoms in the center that need the most bonds, and that of course is invariably carbon. Carbon, because it's in group 4 or 14, they want to make 4 bonds, and so carbon atoms are always in the interior of the molecule. You never want to put them on the end. Hydrogen, on the other hand, because hydrogen can only form 1 bond, the hydrogen atoms have to be on the outside. Oxygen can go either way. Oxygen atoms need 2 bonds, and so they can form 2 single bonds and be in the interior of a molecule, or they can form a double bond and be at the end. So here's one possible skeleton that we might come up with. We've got our carbons in the middle, hydrogen's on the end, and in this case we have oxygen on the end as well. The second step, of course, is to count the valence electrons, and we simply get that from the group number. Hydrogen atoms are in group 1. They each have 1 valence electron, so that's 2. Each carbon atom in group 4 has 4 valence electrons, so that's another 8. Oxygen in group 6 has 6 valence electrons, that's another 6. And that means we have a total of 16 electrons to work with. So by the time we're done with our structure, we should see all 16 of those electrons. The next step is to add the remaining valence electrons. We've used 2, 4, 6, 8 electrons to build our skeleton, so we have 8 left, and we're going to add those as dots, or non-bonding pairs of electrons initially. We'll start with oxygen, because oxygen, being very electronegative, it wants electrons more than pretty much everyone else except fluorine. The oxygen only has 2. It needs 8. So we're going to give oxygen 6 of our 8 remaining valence electrons, and now oxygen has an octet. It's feeling pretty good. Our carbon's not so good. This carbon only has 6, and the one over here only has 4. So we need some additional electrons. We only have 2 left, so it doesn't really matter which carbon we put them on. We'll go and put them on the left-hand carbon. At this point, the carbon on the left has 8. That's good. Oxygen has 8. That's good. But the carbon in the middle only has 4. Whenever we have an atom that is short electrons, the rule of thumb is very simple. For every pair of electrons an atom needs, we have to move a pair of non-bonding electrons from a neighbor and make a bond out of it. So in step 4, we are going to have to make multiple bonds. We'll move this pair of electrons in and make a double bond with the carbon, and that'll get the carbon up to 6. We can move a pair of electrons from oxygen and make another double bond, and now that carbon in the middle will have its desired 8 electrons. So this is our final structure. Each hydrogen has 1 bond. Each carbon has 4 bonds. Oxygen has 2. That's the number of bonds they all want to have. And they also have their octets, other than hydrogen, of course, that gets a duet. So keep in mind, whenever you're drawing a molecule, we have 2 goals. Number 1, get the octet. That's our most important rule. That is a need. We need to do that. As far as this experiment goes, we're always going to give the atoms their octet, or in hydrogen's case, their duet. There are exceptions to the octet rule. Sometimes atoms don't get the number of bonds or the number of electrons that they need for an octet, but that's something for another day. So each atom has the octet. We've met our needs, and the wants, or the desire, is to get the number of bonds the atoms would like to have. If we can accomplish both of those, that's great. We said earlier oxygen atoms want 2 bonds, and it has 2 bonds. Carbon atoms want to form 4 bonds, and they each got their 4 bonds. And hydrogen atoms want 1 bond, and they each got their 1 bond. So this is a perfectly good Lewis structure. Now, it's often possible to come up with more than 1 skeleton for a molecule. If we can do that, then we have formed multiple isomers. Isomers are simply molecules that have the same chemical formula but a different structure. In this case, we could move a hydrogen from the carbon on the left to the oxygen over there on the right, and we can make a different skeleton. This skeleton is still perfectly reasonable. The carbons are in the middle, the hydrogens are on the end, and as we said earlier, oxygen can go either way. It can be on the end or in the middle. Our electron count hasn't changed. We still have those same 16 electrons, and we still need to make sure we add enough to get to 16. So we had those remaining 8 electrons. We put 4 of them on the oxygen this time, so now oxygen has 2, 4, 6, 8, so oxygen is good. The remaining 4 electrons we had left was enough to give each carbon 2, but that wasn't enough to get carbon their octet. Each of these carbons now only has 6 valence electrons, and that means we will have to go to step 4. We're going to need to move this pair of electrons into the middle, and we'll have to do the same with this pair. And when we do that, we end up with a triple bond between the 2 carbon atoms. So we had 2 double bonds in our first structure. We have a triple bond this time. We've still followed all of the rules. Each hydrogen has 1 bond, and they each have their duet, so hydrogen is good. Each carbon has 4 bonds and an octet, so carbon is good. And the oxygen has 2 bonds and an octet as well, so oxygen is also satisfied. These are both real molecules. They both exist, and they simply have the same chemical formula, but different structures or different skeletons. I mentioned in the introduction to the lab that the shapes of molecules is extremely important. Changing the shape or the bond angles in molecules can completely alter their chemical and physical properties. So it's important to chemists to know how to determine what the shape of a molecule will be and what the angles will be between the atoms. So we're going to go through all of the different possibilities that you're going to run into in the lab today. There are more than these, but in introductory chemistry, we're going to be looking at 3 basic different bond angles. So let's start out with a fairly simple molecule, methane CH4. Methane, of course, would have to have carbon in the center and the hydrogens on the outside. Now, if you take a look at this molecule, and I showed you something similar in the introduction, there seems to be a 90-degree angle between those hydrogen atoms. This particular shape is known as a square planar molecule because it's flat and it looks like a square. But the question is, of course, is this the best we can do? The electrons in these 4 bonds want to be as far apart from each other as possible. And as I mentioned in the introduction, 90 degrees isn't really the best we can do because we haven't thought 3-dimensionally. The methane molecule is actually 3-dimensional. It spreads out in the X, Y, and Z axis, and it's pretty obvious if you look at those hydrogen atoms, they are clearly farther apart than 90 degrees. The angle in this particular molecule is actually 109.5 degrees. That's not the type of thing you learn about in a normal geometry class, but that's something you'll simply want to add to your repertoire. You're going to need to know that angle for upcoming quizzes and exams. This particular shape, as we said earlier, is referred to as a tetrahedral geometry, or we refer to this as a tetrahedron, this particular molecule. Tetra, of course, means 4, and hedron refers to sides. You can take any 3 of these hydrogen atoms and you can make a triangle. There's one triangle, there's another, these 3 in the back make a triangle, and the 3 on the bottom make a 4th triangle. So the tetrahedron is simply made of 4 equilateral triangles all connected to one another. Next, let's take a look at the ammonia molecule. Ammonia is similar to the methane molecule. As you recall, in the methane molecule, we had a carbon with 4 hydrogen atoms attached to it. So the carbon was connected to 4 groups. The ammonia molecule is very similar. The nitrogen is attached to 3 hydrogen atoms and a non-bonding pair of electrons. When we determine the shape and the bond angle in a molecule, it's the number of groups attached to the central atom that makes that determination. So the definition of a group is the number of atoms attached to the center plus the number of non-bonding pairs of electrons. In methane, carbon had 4 atoms of hydrogen attached to it. In ammonia, we have 3 atoms of hydrogen and 1 non-bonding pair of electrons. This particular shape is referred to as a T-shaped molecule. When we talk about the shape of a molecule, we don't consider the non-bonding electrons. Think of them as sort of being invisible. They're important because they force the other atoms in the molecule into their position. But if we only look at the atoms here, it sort of looks like a letter T. Again, that only gives us a 90-degree separation between the atoms. So like the methane molecule, the ammonia molecule is going to spread out 3-dimensionally into this tetrahedral type of arrangement. And again, we'll have an angle of approximately 109.5 degrees. The angle won't be exactly 109.5. That only happens if all 4 groups are identical to each other. When there's 2 different kinds of groups, the angle will vary a little bit. Ammonia happens to have a bond angle of 107 degrees. That's not something you need to worry about remembering. We don't actually refer to this molecule anymore as a tetrahedron or a tetrahedral molecule. Remember, we decided that the shapes are based only on the atoms. Even though this non-bonding pair of electrons is important, for the shape we look at the N and the 3 H's. It looks a lot like a tripod. We have the nitrogen at the top and then the 3 hydrogens at the base. It's referred to as a trigonal pyramid. It looks a bit like a pyramid. The nitrogens at the peak or apex of the pyramid and the 3 hydrogens make the base. Unlike an Egyptian pyramid in which there are 4 points at the base, those are known as a square-based pyramid. This is a triangular or a trigonal pyramid. Next, we're going to take a look at the water molecule. The water molecule actually is very similar to the methane and ammonia molecules because, like each of those, the central atom is attached to 4 groups. In this case, there are 2 atoms of hydrogen and 2 non-bonding pairs of electrons. In this particular structure, the hydrogen atoms would be 180 degrees away from each other. And you might think, wow, that's great. We want the atoms to be as far from each other as we can. This particular shape, if we ignore the non-bonding pairs of electrons, the H, the O, and the H form a straight line, and it's referred to as a linear molecule. But once again, we need to think 3-dimensionally. The water molecule is not a flat molecule. If it were, we would only have a 90-degree separation again between each of the atoms and pairs of electrons, and we can do better than that. If we move 3-dimensionally, now our hydrogen atoms or our non-bonding electrons will be 109.5 degrees away from each other, approximately. As I mentioned with the ammonia, the angle will not be exactly 109.5 unless all 4 groups are identical. In the case of water, it's actually 104.5, so it's close. And to keep things simple in the experiment and on our exams and quizzes, we'll just say 109.5. So anytime a molecule has 4 groups, we'll just use 109.5 because there is no easy way to determine what the angle would be, say, in a water molecule unless you looked it up. The water molecule, if we only consider the atoms, is what we would call a bent molecule. When you only have 3 atoms in a molecule, there are only 2 possibilities. They're in a straight line or they're not. If they're in a straight line, you have a linear molecule. If they're not in a straight line, you have a bent molecule. And in the case of water, it will be a bent molecule because that gives us a bigger separation between the pairs of electrons. Remember, these bonds are all pairs of electrons. So these pairs of electrons want to be as far apart from each other as they can be. In each of our first 3 examples, the methane, the ammonia, and the water, the central atom had 4 groups attached to it. But there's not always going to be 4 groups. For example, in sulfur trioxide, there are only 3 groups attached to the sulfur. The oxygen here, one of the oxygens has to have a double bond, so I've indicated that with the 2 lines here. In terms of defining a group, that doesn't matter. Whether an oxygen is double bonded or like these 2 single bonded, it's still one group. So we have 1, 2, 3 groups attached to the sulfur. The bond angle between the oxygens here is 90 degrees. And again, perhaps we can do better than that. This particular shape, as we mentioned a bit earlier, is known as a T-shaped molecule, but it's possible for these things to spread out even further. The sulfur trioxide molecule actually spreads out such that you get a 120 degree angle between the atoms. Imagine this is a circle, 360 degrees, and we divided it into thirds, so each of those angles is a 120 degree angle. This particular shape is known as a trigonal planar molecule. Again, it's trigonal because of the 3 oxygens, and it's planar because it's a flat plane. So with 3 groups, the best we can do is a 120 degree separation. And that makes sense. The more groups you put around the center, the closer they'll have to be together. So when there were 4 groups around the center, the best we could do was 109.5 degrees. Now with only 3 groups around the center, we can get farther apart, and now we have a bond angle of 120 degrees. Like sulfur trioxide, sulfur dioxide also has 3 groups. In this case, one of the oxygens has now been replaced with a non-bonding pair of electrons. So we have 2 oxygen atoms and a non-bonding pair of electrons. In this particular structure, the angle is still 90 degrees between the oxygens. If we only look at the atoms and ignore the non-bonding pair of electrons, we come up with what's known as a bent geometry, much like the water molecule. As I had said previously, if you have 3 atoms connected to one another, there's only 2 possibilities. The molecule is either bent or it's linear. Again, we can do better. Like sulfur trioxide, sulfur dioxide spreads out into a 120 degree angle. It still looks like a trigonal planar arrangement, but one of the points is a non-bonding pair of electrons. If we only look at the atoms then, we have a bent molecule, but it's not bent at 90 degrees as our first structure showed, it's bent at 120 degrees. So again, with only 3 groups surrounding the sulfur instead of 4, we can spread out to a greater angle. So bent can mean different things. In the water molecule, bent was 109.5 degrees. In sulfur dioxide, bent is 120 degrees. Finally, we're going to wrap things up with carbon dioxide. Carbon dioxide only has 2 groups attached to the carbon. The carbon atoms almost never have non-bonding electrons. So if you're ever drawing a Lewis structure and you've got dots or non-bonding electrons on carbon, you've probably made a mistake. So the carbon atom gets its octet from 2 double bonds with the oxygens. So because there are no non-bonding electrons, the molecule is in a nice straight line, and we get a 180-degree angle. Again, with 4 groups, they're closer together. That was 109.5 degrees. With 3 groups, we got a little farther apart, 120 degrees, and with only 2 groups attached to the center, we can reach a separation of 180 degrees. So this molecule truly is a linear molecule. The earlier ones that we call linear were only that way when we hadn't actually thought about 3-dimensional shapes. So these are the basic shapes and angles of molecules you're going to run into in the lab today. So let's go ahead and summarize this. Let's take a look at the 6 things we've looked at here. First, we had the methane molecule, which formed a tetrahedron and has an angle of 109.5 degrees. You'll see that quite commonly in today's lab. Then we had the ammonia molecule, which had only 3 atoms attached to the center and our invisible non-bonding pair of electrons. So this gave us a trigonal pyramid and a 109.5 degree angle approximately. And finally, the last example we had with 4 groups was the water molecule, which is a bent molecule because there are 2 hydrogen atoms and those 2 invisible non-bonding pairs of electrons. And again, it's approximately 109.5 degrees. So these are the 3 cases in which you have 4 groups attached to the center. We have 4 atoms, 3 atoms and a non-bonding pair of electrons, or 2 atoms and 2 non-bonding pairs of electrons. We then moved on to the examples where there were 3 groups. The first one we looked at was sulfur trioxide, and with 3 groups we end up with a trigonal planar arrangement and a 120-degree angle. Sulfur dioxide actually looked a lot like the water molecule. We had, in this case, however, 2 atoms and only 1 non-bonding pair of electrons. So with 3 groups, it was able to spread out more. And it's approximately 120 degrees. Again, because the 3 groups aren't identical, it's not exactly 120, it's more like 118 degrees. And finally, the one we just talked about, carbon dioxide, with only 2 groups, we have a linear molecule, and the bond angle will be 180 degrees. The molecules we've been looking at so far have been fairly simple because they only have 1 angle. But it is possible for molecules to have more than 1 angle. In fact, they can have all 3, the 109.5, the 120, and the 180. So let's take a look at those first 2 structures we drew at the beginning. In this particular molecule, we have 3 atoms in the interior, and each of those atoms will have their own angle. This carbon, for example, is attached to 2 groups. It has a 180-degree angle. The other carbon is also attached to 2 groups. It also has a 180-degree angle. The oxygen is attached to 4 groups, so it will have a 109.5-degree angle. The names we've given to molecules, like linear and tetrahedral and such, don't really work when there's more than 1 angle, and so we don't normally worry about using those. This molecule is both linear and bent, and since we can't have a particular name for it, we will simply make sure we label all the angles appropriately. In the lab today, the very last example you'll be doing, C6H6, has many, many different possible isomers. Some of those isomers will have all 3 of the angles, so make sure you label each angle if they're not all going to be the same. Our other isomer from the beginning was a little bit different. Now there's only 2 atoms in the center. The carbon on the left side has 1, 2, 3 groups attached to it. It has a 120-degree angle. The carbon in the right side has only 2 groups attached to it, therefore it's going to have a 180-degree angle. So the angles in these 2 isomers will be different. We're just about ready now to get started on the lab exercise. There are 3 pages of structures that you'll be drawing. There's a box for a simple sketch in which you're going to just sort of sketch out the skeleton and the basic shape of the molecule, and then I want you to try to draw a more accurate 3-dimensional sketch in which you also label the bond angles. There are then some questions at the end, and one of those questions is going to take you a little bit beyond what we've been doing here, because it's going to have more than 4 groups attached to it. In Chem 3A, we normally only work with molecules that have 2, 3, or 4 groups, but it's possible to go well beyond that. And so question number 2 in the lab is going to have you use your imagination and see if you can come up with a structure for a molecule that has 6 groups attached to it. I think that's all the background information you need, so go ahead and get to work on the lab. And once you're done, go ahead and submit that.